Hello, in this lecture we will find out the area of the green triangle. In the drawing we have a quarter circle. A or B is a quarter circle. Inside the quarter circle we have line segment PQ that is equal to 3 units. Line segment AQ equals to 5 units. And this angle APQ is equal to 90 degrees. Our mission is to find out the area of the green right triangle AQO. So we'll focus on the right triangle APQ. Again, we'll focus on the right yellow triangle APQ, and we'll implement the Pythagoras theorem on this right yellow triangle APQ. Okay, so here we have triangle APQ, the yellow triangle APQ by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse, the right yellow triangle APQ is AQ, therefore the square of the hypotenuse is AQ square. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to PQ square plus PA square. Repeat again. In the right yellow triangle APQ, according to the Pythagoras theorem, AQ square equals to PQ square plus PA square. AQ is 5, therefore AQ square is 5 squared, that is 25, and it is equal to PQ square. PQ is 3, and so PQ square is 3 squared, that is 9, plus PA square. So I found out that 25 equals to 9 plus PA square according to the Pythagoras theorem in the right triangle APQ. We subtract 9 from this equation, and we get that 25 minus 9 is 16. It is equal to PA square. Here we take out of this equation, and finally we get that PA equals to the square root of 16, that is 4. So here, line segment PA equals to 4 units in its length. This line segment PA equals to 4 units. So A or B is a quarter circle. You can easily complete the quarter circle to a circle, and then point O will be the center of the circle. Again, if we complete the quarter circle to a circle, point O will be the center of the circle. And we have rule number 2, that a perpendicular from the center of the circle towards any chord bisects the chord. I'll repeat the rule number 2 again. According to rule number 2, a perpendicular from the center of a circle towards any chord bisects the chord. Point O is the center of this circle. If from point O we draw perpendicular towards chord BC, it will bisect chord BC. So from point O we draw perpendicular to BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. Then we define the touching point of the perpendicular from point O and chord BC as M. So according to this rule number 2, the perpendicular OM bisects chord BC. Again, the perpendicular OM bisects chord BC. That is to say, divide it into two halves. The first half is BM, and the second half is MC. And of course, BM equals to MC. So we can implement rule number 2 in our drawing. From point O, that is the center of the circle, we will draw perpendicular to PA, to chord PA. Actually, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord PA as M. According to rule number 2, the perpendicular OM bisects chord PA. And because of the fact that PA equals to 4 units, then according to number 2, the perpendicular OM bisects chord PA, that is to say, PM is the first half, therefore it is equal to 2 units, and MA is the second half of PM, therefore it is equal to 2 units also. In the next step, we'll define the intersection point between the perpendicular OM and line segment QA as N. We define angle PAQ as theta. If we focus on the right yellow triangle AMN, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. Exactly according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, if we focus on the right big yellow triangle APQ, this right yellow triangle, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we will prove that the small right yellow triangle AMN is similar to the big right yellow triangle APQ. So the big right yellow triangle APQ is similar to the small white yellow triangle AMN. So why those two white yellow triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this angle APQ in the big triangle is equal to this angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. Repeat again. Angle APQ in the big triangle is equal to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta is a common angle that belongs to both triangles. You can see here that angle theta belongs to the right triangle AMN, and angle theta also belongs to the right triangle APQ. Therefore, we will write down that angle theta is equal to itself. Okay, so angle theta, if we relate to angle theta as it is belong to the big triangle, then we get that angle theta will be defined as angle PAQ. And if we relate to angle theta as it is belongs to the small triangle MAN, angle theta will be angle MAN. Angle theta is the common angle that belongs to both triangles. Therefore, angle theta equals to itself. Again, in the big triangle, angle theta is defined as angle PAQ, and it is equal to angle theta itself. In the small triangle, angle theta is defined as angle MAN. Again, angle theta is the common angle that belongs to both triangles, therefore angle theta equals to itself. And finally, those two angles that are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle AQP in the big triangle this angle equals to angle ANM in the small triangle, this angle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. Angle AQP in the big triangle is equal to angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the triangles in the big triangle are correspondingly equal to all the triangles in the small triangle. Therefore we proved that the two triangles are similar to each other according to angle similarity rule. So I'll write it down. Triangle, the big triangle APQ is similar, this is the sign of similar, to the small triangle AMN according to angle similarity rule. What is angle similarity rule? Angle similarity rule means that if you prove that all three angles in one triangle are correspondingly equal to all the angles in another triangle, then you actually proved that the two triangles are similar to each other according to angle similarity rule. And from the fact that those two white yellow triangles are similar to each other, we will conclude that the following relationship exists between their sides. We conclude and derive that PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is equal to QA in the big triangle over NA in the small triangle. So I will write it down. PA with the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is also equals to QA in the big triangle over NA in the small triangle. So I'll repeat again. PA over MA equals to PQ over MN equals to QA over NA. PA is 4 over MA is 2, and it is equal to PQ is 3 over MN that is unknown, so we leave it as it is, and it is equal to QA is 5 over NA that is unknown, so we leave it as it is. In conclusion, found out that 4 over 2 equals to 3 over mn equals to 5 over na. From this equation we will derive that 4 over 2 equals to 3 over mn. 4 over 2 is 2, so 2 equals to 3 over mn. Here we multiply this equation by mn, and we get that 2 times mn equals to 3. We'll divide this equation by 2, and finally we'll get that mn equals to 3 over 2. 3 over 2 is 1.5. So the length of line segment mn is 1.5 units. So I'll write it down in the drawing. That mn equals to 1.5 units in its length. So this line segment mn equals to 1.5 units in its length. From the same equation, we will derive that 4 over 2 equals to 5 over na. Again, 4 over 2 equals to 5 over na. Four over 2 equals to 5 over na. 4 over 2 is 2, so 2 equals to 5 over na. We multiply this equation by na, and we will get that 2 times na equals to 5. We'll divide this equation by 2, and finally we will get that na equals to 5 over 2. 5 over 2 is 2.5. So if we found out that the length of line segment NA is equal to 2.5 units. This line segment NA equals to 2.5 units. And what is the length of line segment QN? From the drawing it is very easy to see that QN equals to QA minus NA. Again, Qn equals to Qa minus Na. Qn equals to Qa minus Na. So Qn equals to Qa is 5 and Na is 2.5. So it is minus Na, that is 2.5. So Qn equals to 5 minus 2.5, that is 2.5. So Qn equals to 2.5 units in its length. We know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. Therefore, we block the right green triangle AOQ by a circle. So I'll copy the right green triangle AOQ in the new page and we will block it by a circle. So actually, this is the right green triangle AOQ that I copied from the original drawing. Now we will block this triangle by a circle. Inside this circle, we have peripheral angle A or Q that is equal to 90 degrees. I'll write it down. And we have rule number 5 that states that any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. I'll repeat again on rule number 5. According to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Okay. Here, peripheral angle ABC, it is equal to 90 degrees in its size. Therefore, this peripheral angle ABC rests on the diameter of the circle. The diameter of the circle is AC. So, peripheral angle ABC that is equal to 90 degrees rests on AC, that is the diameter of the circle. You can implement rule number 5 in our drawing. Why? Because in our drawing, we have peripheral angle ABC, peripheral angle A or Q that is equal to 90 degrees. Therefore, this peripheral angle rests on the diameter of the circle. That is to say, QA is the diameter of the circle. And we also know that the diameter of any circle is twice as long as the radius, so the diameter equals to 2 times the radius times r. From one side, from the other side, it is given as an equation that QA equals to 5 units in its length. And from this equation, we will derive that 5 equals to 2r. 5 equals to 2r. Here we'll divide this equation by 2, and finally we get that the radius of this circle r, it is equal to 2.5 units. R equals to 2.5 units. So this is the right triangle AOQ that I call it from the original drawing. Okay. This is exactly the same right triangle AOQ, again right triangle. So in the next step I will copy point N from the original drawing from here to our drawing here. We take point N exactly where it is located on QA, and we'll put it here. So actually this is point N that I copied from the original drawing. We have already found out that AN equals to 2.5 units in its length, and line segment NQ also equals to 2.5 units in its length. QA is the diameter of the circle. We just right now found out that the radius of this circle R is equals to 2.5 units. So line segment NA is located on the diameter of the circle, that is to say on QA, and it is equal to 2.5 units. But the radius of this circle also equals to 2.5 units. Therefore, therefore line segment NA must be the radius of the circle. Likewise, NQ is located on the diameter of the circle, and it is equal to 2.5 units, but the radius also equals to 2.5 units. Therefore, NQ must be the radius of the circle, where is the center? Where is the center of this circle? Where it is located along the diameter QA. We have the rule that the center of any circle is located at a point where the diameter is bisected into two halves. Okay? The center of any circle is located at a point where the diameter is bisected into two halves. And because of the fact that QA in total equals to 5 units, the first half will be equal to 2.5 units, and the second half will be also be equal to 2.5 units. So the first half is AN that is equal to 2.5 units, and the second half is NQ that is also equals to 2.5 units. So that is to say at point N, the diameter QA is bisected into two halves. Therefore point N is the center of the circle. Point N is the center of the circle. Another reason that point N is the center of the circle is because of the fact that the center of any circle is located at the point where the two radii touch each other, or where the radii touch each other, or where the two radii touch each other. Here, the first radius of this circle is AN. That's not the radius AN starts from point N, and that's at point N. The second radius of this circle is QN. That starts from point Q, and ends at point N. That is to say, the two radii touch each other at point N. Point N is the touching point of those two radii. That is a second reason why point N is the center of this circle. So we join points N and O together by a straight line. Point N is the center of the circle, point O is the point of the circle itself. This is exactly the definition of a radius, therefore NO is the radius of the circle that is equal to 2.5 units. So here, line 7 NO is the radius of the circle that is equal to 2.5 units in its length. In the next step, I will copy the right triangle AMO in a new page, and we will implement on this right triangle the Pythagoras theorem. Side AM equals to 2 units in its length. What is the length of side MO? From the drawing is already to see that MO equals to MN plus NO. So MO equals to MN, that is 1.5, plus NO, that is 2.5. In total, MO equals to 1.5 plus 2.5, this is 4. So actually, this is the right triangle AO that I copied from the original drawing. MA equals to 2, MO equals to 4. So here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, and this right triangle AO squared equals to MA squared plus MO squared. So AO squared equals to ma square. Ma is 2, therefore ma square is 2 squared, that is 4, plus mo square. Mo is 4, therefore mo square is 4 squared, that is 16. So ao square equals to 4 plus 16, that is 20. We'll take out of this equation, and finally we will get that ao equals to the square root of 20 units. So I write it down in the original drawing that ao equals to the square root of 20 units. And it's there. AO equals to the square root of 20 units. In the next step, I'll copy the right green triangle AQO in a new page and we'll implement in this right green triangle the Pythagoras theorem. AO equals to the square root of 20 units in its length. The hypotenuse AQ equals to 5 units. So actually, this is the right triangle AOQ that I copied from the original drawing. According to the Pythagoras theorem, this right triangle AOQ, AQ square equals to AO square plus QO square. Again, AQ square equals to AO square plus QO square according to the Pythagoras theorem. AQ is 5, therefore AQ square is 5 squared, that is 25. And is equal to AO square. AO is square root of 20, therefore AO square is square root of 20 squared, that is 20, plus QO square. Here we'll subtract 20 from this equation and we get that 25 minus 20 is 5. That's equal to QO square. We'll take out of this equation and finally we get that QO equals to the square root of 5 units in its length. QO equals to the square root of 5 units. I'll write it down the original drawing that QO equals to the square root of 5 units in its length. Now it is very easy to find out the area of the right triangle AQO. That is the area that we are looking for. So in the right triangle AOQ, according to the Pythagoras theorem, so I put in the right triangle AQO, the area of the right green triangle AQO, it is equal, here, the square brackets is the same for the area, it means the area of triangle AOQ. It is equal, we know that the area of any triangle, it is equal to the base of the triangle times the height to the base. The height must create 90 degrees with the base, over 2. So we take the base of this right triangle as QO. This is the base. The height is AO. Why the height is AO? Because it creates 90 degrees with the base QO. This angle equals to 90 degrees. So the height is AO over 2. Repeat again. The base is QO, the height is AO over 2. QO, it is equal to square root of 5 units. AO, it is equal to the square root of 20 units divided by 2. QO is equal to 5, AO is equal to 20 over 2. We have the algebraic identity that says that the square root of A times square root of B equals to the square root of AB. According to this trigonometric identity, we get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 over 2. 5 times 20 is 100. So inside the root we have 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. So finally we found out that the area of the green right triangle AQO is equal to 5 square units. Repeat again. The area of this right triangle AQO, right green triangle AQO, is equal to 5 square units. In the next step, I will summarize the lecture. In this lecture, we found out the area of the right triangle AQO. We know that PQ equals to 4 units in its length, AQ equals to 5 units in its length, and this angle APQ equals to 90 degrees. Again, our mission is to find out the area of this right great triangle AQO. We focused on the right triangle APQ and the right yellow triangle APQ. We implemented in this right yellow triangle APQ the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AQ, therefore the square of the hypotenuse is AQ squared. It must be equal to PQ squared plus PA squared. Repeat again. According to the Pythagoras theorem, in the right yellow triangle APQ, AQ squared equals to PQ squared plus PA squared. AQ is 5, therefore AQ squared is 5 squared, that is 25, plus PQ squared. PQ is 3, therefore PQ squared is 3 squared, that is 9, plus PA squared. We subtracted 9 from this equation. We found out 25 minus 9 is 16, so 16 equals to PA squared. Took a root out of this equation, and finally we found out that PA equals to the square root of 16, that is 4. So this line segment PA equals to 4 units in its length. Then we know that AOB is a quarter circle. If we complete the quarter circle to a circle, then point O will be the center of this circle. And we have rule number 2 that a perpendicular from the center of the circle towards any chord bisects the chord. I repeat again rule number 2. A perpendicular from the center of a circle towards any chord bisects the chord. Point O is the center of the circle. BC is a chord, so from the center of the circle, that is to say from point O, if we draw a perpendicular to BC, this angle is 90 degrees, this angle is 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord BC as M. So according to rule number 2, the perpendicular OM bisects chord BC. Again, the perpendicular OM bisects chord BC. That is to say, it divides it into 2 halves. The first half is BM, the second half is MC. And of course, they are equal to each other. BM equals to MC. Okay, so we can implement rule number 2 in our drawing. In our drawing, from the center of this circle, the circle, that is to say from point O, we draw perpendicular towards chord PA. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and PA as M. So according to rule number 2, the perpendicular OM bisects chord PA. Again, the perpendicular OM bisects chord PA. That is to say, divide this into 2 halves. The first half is PM and the second half is MA. And because of the fact that PA equals to 4, it means that the first half PM will be equal to 2 units and the second half MA also will be equal to 2 units. Then we defined the intersection point between perpendicular OM and line segment QA as N. Then we define this angle PAQ as theta. If we focus on this triangle AMN, right yellow triangle AMN, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees, exactly according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the right triangle APQ, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle, this angle must be equal to 90 degrees minus theta. Then we prove that the right small yellow triangle AMN is similar to the right triangle APQ. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. Again, angle APQ in the big triangle is equal to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, angle theta is a common angle that belongs to both triangles. So angle theta equals to itself. Angle theta is angle PAQ, and angle theta is also angle AMN. We call to angle theta two different names. So angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle AQP in the big triangle is equal to angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So I actually proved that all three angles in the big triangles are correspondingly equal to all the three angles in the small triangle. Therefore, the two right yellow triangles are similar to each other according to angle similarity rule. The big triangle APQ is similar, this is the sign of similar, to the small triangle AMN according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all the angles in one triangle are correspondingly equal to all the angles in another triangle, then you have fully proved that the two triangles are similar to each other according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We conclude that PA in the big triangle over MA in the small triangle is equal to PQ in the big triangle over MN in the small triangle, and it is equal to QA in the big triangle over NA in the small triangle. I'll repeat again. PA over MA equals to PQ over MN equals to QA over AN. PA is 4, MN is 2, PQ is 3, MN is unknown, QA is 5, and AN is unknown. From this equation, we derive that 4 over 2 equals to 3 over MN. Again, 4 over 2 is equal to 3 over MN. 4 over 2 is 2, so 2 equals to 3 over MN. We multiply this equation by 2, and finally we got that 2 times MN equals to 3. We divided this equation by 2, and we found out that MN equals to 3 over 2. 3 over 2 is 1.5. So the length of this line segment MN is 1.5 units. From the same equation, this equation we derive that 4 over 2 is equal to 5 over NA. Again, 4 over 2 is equal to 5 over NA. 4 over 2 is 2, so 2 equals to 5 over NA. We multiply this equation by NA, and we got that 2 times NA is 5, is equal to 5. We divided this equation by 2, and finally we got that NA equals to 5 over 2, that is 2.5 units. This line segment N8 is equal to 2.5 units in its length. What is the length of line segment QN? From the drawing, it is very easy to see that QN equals to QA minus NA. Again, QN equals to QA minus NA. Again, QN is equal to QA minus NA. QA is 5 and NA is 2.5. Therefore, QN in total equals to 5 minus 2.5. That is 2.5. So the length of this line segment QN is 2.5 units. We know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. Therefore, we block the right green triangle AQO by a circle. So I call it the right green triangle AQO in a new question. This is triangle AQO that I call it on the original drawing. And we block this triangle by a circle. Okay. In this circle, we have peripheral angle AOQ that is equal to 90 degrees. And we have rule number 5 that states that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. I'll repeat again on rule number 5. According to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Here, peripheral angle ABC equals to 90 degrees. Therefore, peripheral angle ABC rests on AC, that is the diameter of the circle. We implemented 1/5 in our drawing. Because of the fact that peripheral angle AOQ rests, AOQ it is equal to 90 degrees, therefore it rests on the diameter of the circle, that is to say AQ is the diameter of the circle. We know that the diameter of any circle is twice as long as the radius. So the diameter of this circle will be equal to 2 times the radius, to R. From one side, from the other side, it is given as the equation that QA equals to 5 units. And from this equation, we derive that 5 equals to 2R. We divided this equation by 2, and finally we got that the radius of this circle, it is equal to 2.5 units. In the next step, so this is the right triangle AQO that I copied from the original drawing. Again, right triangle AQO. In the next step, I copied point N exactly where it is located along the diameter QA to this drawing. Okay, so I copied point N from the original drawing. We already found out that N equals to 2.5 units and Q also equals to 2.5 units. Okay, we found out that QA is the diameter. AN is located on the diameter and it is equal to 2.5 units, but the radius of the circle also equals to 2.5 units. Therefore, AN must be the radius of the circle that is equal to 2.5 units. Likewise, NQ is equal to 2.5 units. But the radius of this circle also equals to 2.5 units, and NQ is located on the diameter. Therefore, NQ must be also the radius of the circle that is equal to 2.5 units. Okay, so we have here the two radii of the circle, AN and NQ. Where is the center of this circle? According to the rule that the center of any circle is located at a point where the diameter is bisected into two halves. Again, the center of any circle is located at a point where the diameter is bisected into two halves. Because of the fact that the diameter AQ is equal to 5 units, 1/2 of the diameter, it is actually 5/2, that is 2.5. What is happening is point N? At point N, indeed, the diameter is bisected into two halves. Why? Because the first half is AN, that is 2.5, and the second half is NQ, that is also 2.5 units. That is to say, N is the center of the circle. Okay? For that point N, the diameter is bisected into two halves. That is one reason that point N is the center of the circle. A second reason that point N is the center of the circle, because of the fact that the center of any circle is located at a point where the radii touch each other. What is happening in point N? We have the radius AN that starts from point N and ends at point N. It starts from point N and ends at point N. From one side, but from the other side, the other radius QN also starts at point Q and ends at point N. That is to say, point N is the touching point of the two radii. At point N, the two radii touch each other. Therefore, point N must be the radius of this circle. Point N is the center of the circle. We have two reasons why point N is the center of the circle. Okay, point N is the center of the circle. We join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is the point of the circle itself. This is exactly the definition of a radius. Therefore, NO is the radius of the circle, that is equal to 2.5 units here. NO, it is the radius of the circle, that is equal to 2.5 units. Then, I copied the right triangle AMO in the new page and implemented in this right triangle AMO the Pythagoras theorem. Line segment AM or side AM equals to 2 units in length. Side MO equals to MN plus NO. MN is 1.5, NO is 2.5. Therefore, in total, MO equals to 1.5 plus 2.5, that is 4. So this is the right triangle AMO that are coming from the original drawing. Again, MA is 2, MO is 4. By PT is a version for Pythagoras theorem. According to the Pythagoras theorem, AO square equals to AM square plus MO square. Again, AO square equals to AM square plus MO square. AO square equals to MA square. MA is 2, therefore MA square is 2 square, that is 4. Plus MO square. MO is 4, therefore MO square is 4 square, that is 16. In conclusion, found out that AO square equals to 4 plus 16, that is 20. Then we took a root out of this equation. And finally found out that AO equals to the square root of 20. So I can write down here that AO equals to the square root of 20 units in its length. Then I copied the right angle triangle AQO in a new page and implemented this right angle triangle AOQ, the Pythagoras theorem. This is actually the right triangle that I copied from the original drawing. AO equals to the square root of 20 units, the hypotenuse QO equals to 5 units in its length, and according to the Pythagoras theorem, here by PT is a version for Pythagoras theorem. AQ square equals to AO square plus QO square. Again, AQ square equals to AO square plus QO square. AQ is 5, therefore Q square is 5 square, that is 25. That is equal to AO square. AO is square root of 20, therefore AO square is square root of 20 square, that is 20 plus QO square. We subtracted 20 from this equation and found out that 25 minus 20 is 5, so 5 equals to QO square. We took a root out of this equation and finally found out that QO equals to the square root of 5 units. Here QO equals to the square root of 5 units. So I can write down the original drawing that QO equals to the square root of 5 units. Now it is very easy to find out the area of the right triangle AQO, that is the area that we are looking for. Here the square brackets is the sign for the area. It's the area of triangle AQO. The area of any triangle, it is equal to the base of the triangle times the height to the base over 2. The height once creates 90 degrees is the base. So the base is QO, the height to the base is AO, why? Because the height AO creates 90 degrees with the base QO. Here, this area is 90 degrees. Again, the base is QO, the height is AO over 2. QO equals to the square root of 5 units. AO equals to the square root of 20 units. Over 2. We have the algebraic identity that the square root of A times square root of B equals to the square root of A times B. According to this algebraic identity, we will get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 over 2. 5 times 20 is 100, so inside the root we have only 100 over 2. The square root of 100 is 10 and 10 over 2 is 5. So actually found out that the area of this green right triangle AQO, that is the area that we are looking for, it is equal to 5 square units. Okay? The area of this green triangle is 5 square units. Okay? Thank you very much.